Hey, homework? Yes. Oh, yeah, you can turn it in. Yeah, if you guys are submitting your homework in person, you can turn it in up here. Mhm. You can just hold the pointer. You. Hey. All right, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Good, good. How's the audio on Zoom, guys? I'm trying a new setup just so I don't have to lug my laptop around everywhere. So I'm using the console computer. So can everyone on Zoom hear me okay? Great, awesome. Yeah, I think the webcam here is a little bit higher quality too. I think that'll help a bit. So and so that's kind of why I had to update the Zoom link. It's so because I had to set up cloud recording because I don't want it to download. I don't want it to record and download onto this computer because I'm just going to be leaving right afterwards. So and so thank you guys for using the new Zoom link and and fixing everything right there. Okay. So today we have a short week this week. So obviously we didn't have lecture on Monday. And so the plan for today is we're going to finish up kind of the last bits of our review on strength of materials. Okay? So that's not too much to there. And so I kind of want to cut that short a little bit because I do want to get into the new stuff. And so today we're going to be after that, we're going to starting our lecture notes on bone biomechanics. Okay. And so I think this is kind of our first kind of big real unit in this class, because up to this point we've mostly been doing review. And I can kind of feel that it's been a little bit boring. And so, that's why I kind of wanted to accelerate the review stuff and kind of get to the newer stuff. So, to make this class a little bit more exciting, because it's an elective after all. And so it should be something more, lots of really new and exciting information. Okay, so before we begin, a couple announcements. Homework 1 is due today. And so if you have it in person, you want to turn it in, you can come up here. If not, you can submit the PDF on Canvas, and I think it's not due until 11:59 p.m. tonight. Okay, and so make sure you get that in, before the deadline, and then I will grade it probably on Friday. Okay? I did post the second homework, and so the second homework is up there, and so that's going to be due on Monday, September 20th, and so you have about 10 days for it. Right? It is quite a bit longer than the first assignment because I am trying something a little bit new for this assignment. Just because I after reading a lot of your introduction emails, a lot of you guys are really interested in a very wide kind of range of topics within biomechanics, which is great. I think it's really cool that you guys are coming in here with a good idea for what you want to learn. The problem is we really just don't have enough time in one semester to cover absolutely everything that's covered out there, and so. I don't know if I'm going to make this a regular thing or maybe I'll make it every other homework assignment. But for homework 2, what I'm going to have you guys do is to do kind of like a mini research project. And so I gave you guys kind of a fairly specialized topic in biomechanics. This time is something related to bone, and I want you guys to do a little bit of research into the primary literature. So look up some scientific articles, see what you can find out there, and then write kind of a brief kind of 2-page report on it. Okay. And so I'm not sure how long, usually those things, they seem easier than it is. And so I want to make sure I give you guys advanced warning for that and enough time to complete it. So, make sure you start that early. And so you can, do your research and then write the report after that. Okay. And, and based on what you guys tell me about it, maybe it's something I'll make a regular thing, or maybe it's something, we only do every now and then. But I also find that it's going to be a good warm up for the final project too, because the final project is going to be of a similar nature, or at least the way I envisioned it. So the final project, I also want you guys to kind of do like an independent research project, but on a much bigger scale than this. So your final report will be much longer than just 2 pages, but it'll be a lot of the same. You'll be doing a lot of the same tasks, like looking up into the literature, reading articles, and using that to write a report. Okay. So make sure to take a look at that, sooner rather than later, and then, let me know if you have any questions. Okay. All right, and so that's it for the announcements. And so, are there any questions just on the homeworks or anything I can answer before we get started? Okay. All right, so let's go ahead and get rolling. I do like the fact that I don't have to bring up my laptop and I have more space to write here, but for for the in-person crew, I have this big ass monitor in my face, and so that I don't like. But so we'll kind of see how this goes. Okay, and so let's go ahead and finish up our review of strength of materials. Okay. And so last time I think we left off talking about the concept of stress, right? Okay. And so there's really kind of two main concepts that I want you guys to take away from this review, and that's the concept of stress and strain. Okay. And so stress, as we talked about before, these are basically internal forces that develop within a structure. Okay. And these internal forces develop whenever a structure is exposed to any kind of external loads. Okay. And their primary purpose is to make sure that the structure maintains equilibrium at all parts of the structure. Okay. And so the simple example that we did last time was we did a kind of a rod, right? Right. And so if we pull on this rod in tension on both sides, okay, so we apply the same load T in opposite directions, then we know that this rod as a whole is in static equilibrium, right? But then if you slice the rod on the interior, this section also has to be in static equilibrium. And so in order to maintain that, some internal stresses here have to develop. Okay. Okay. And so why do we care about this in biomechanics? And so in biomechanics, especially when we start to talk about bones, biomechanics, remember, is just an application of all these principles to biological systems, right? And so, where stress is relevant for biomechanics is that it helps us determine, whether a bone or whether it's a ligament or any kind of tissue, whether that thing will fail. Okay. Okay. Because every material, and bone and tissue are no exception, have this parameter called the yield strength. Okay. Okay. And the units for the yield strength are the exact same as stress. Okay. And so if the internal stress within a structure ever exceeds the yield strength, then we know the structure is going to fail. Okay. And so as an example, or just kind of a visual example here, right? And so when you get a broken bone or when you get a fracture, what happened there was that, your body sustained some kind of large external load, and it sustained it in a way that the internal stress within the bone exceeded its yield strength. Okay. Right. And so bone is actually, quite a bit more complicated than your typical engineering materials, but, it still kind of behaves the same way. And so whenever you stress it past yielding, then it's going to break. Okay. All right. And so last time, I know we started talking about the 6 components of the stress tensor, but, I'm going to just kind of skip over that for now, just because, I thought a bit more about, what I want you guys to take away from this. And, I think talking about the stress tensor and all the different components gets a little bit too into the weeds for, what we're going to do. So, I kind of want to leave our discussion of stress here, and then we'll take this and we'll start to talk about some biological stuff. Okay. Okay. So any questions on this so far? Okay. All right. So that's stress. And so now let's talk about strain. Right. And so strain is typically how we characterize deformations within an elastic structure. Okay. And so in terms of units, it has no units. Okay. Because the way strain is defined is that it's defined as a change in length divided by its original length. So it's basically a relative change in length. Okay. And so I think the simplest example that we can have here is, let's say that we have some kind of rod, okay? And so if we pull on the rod, let's say that our rod has some initial length L, okay? And then after pulling on the rod is going to extend, okay? So I'm making it very exaggerated here. And so normally, you won't see a rod extend this much unless it's made of cheese or something, okay? Okay, and so there's the original length. That's the increase in length, okay? And so usually we call an increase in length or a decrease in length, we call that delta L. Right? And then from here, the strain, which is usually given the symbol epsilon. The strain is given by delta L divided by L. And so since, we have a length divided by a length, then this whole quantity here is units. Okay. All right. Any questions on this? Well, probably you guys have seen strain before in your previous classes. Okay. All right, so that's strain. And so, we have two kind of key concepts in strength of materials here. So we have stress and strain. It turns out that these two guys are very closely related. Okay. The exact nature of their relationship depends on the type of material that you're looking at. Okay. Okay. But in the simplest case, we have what's called a linear material. I should say linear isotropic. Okay. And so in these materials, the stress and strain are linearly related. Okay. And so we have stress is equal to some number multiplied by the strain. Okay. And this particular relationship here is known as Hooke's law. Or a very simple case of Hooke's law. Okay. And so for a linear material, we can draw up a stress strain curve. Okay. And so if we have stress on the x-axis and or strain on the x-axis and stress on the y-axis, a linear material will just go straight up just like that. Okay. Where the slope of this line is E, where E here is the Young's modulus of the material. Okay. All right, so that's stress and strain and how they're related. Okay. A linear material is usually the nicest one to work with because it's simple, right? And so once you know the strain, all you have to do is just multiply it by the Young's modulus, and then that will give you stress. Okay. The unfortunate thing is that we'll almost never see this relationship for any kind of biological materials. Okay. Because biological materials, they're mostly composites of lots of different types of chemical constituents. And so you'll very rarely see this kind of nice relationship, okay? And so, next we'll be going over bones. And so bones, I'll show you probably later on today, that bones actually follow a law called either they're going to be anisotropic or they're going to be orthotropic. And so those are kind of the two different ways stress and strains are related in bones. And we'll talk about what that looks like later on, okay? Okay. Any questions on this before we move on to bone biomechanics? Okay. All right, and so that's it for review. And so I had a lot of review planned for this class, but I realized that it's week 3 already, and we're still doing review. So I should probably cut it short now, right? And so finally, we're going to get into some kind of new exciting stuff, right? And so let's start with bones. Okay. And so the way I kind of structured the next few weeks is that we're going to talk about kind of the 3 main, I would say, kind of structural components within a human body. And so we're going to start with bones this week, and it's going to go into next week. And then after that, we're going to talk about muscles, and then after that, we're going to talk about joints. Okay. And so we're going to talk about kind of the general qualities of these kinds of tissues. Okay. And then after that, we're going to spend the next three or so weeks talking about kind of specific body parts. Okay. And so with the knowledge that we'll have about bones, about muscles and joints, we'll see how that actually applies to, say, your shoulder or your arm or your knee or your hip. Okay. And so, hopefully, so the next few weeks should be pretty exciting because it's fun new stuff. Okay. But we're going to start with the bone, okay? Because I think the bones are kind of the simplest of the tissues to look at within the body. Okay. And just like we talked about in the very first week of class, bones have the important function of providing structure and rigidity to the body. Okay. Right. And so the first purpose that they serve is that they provide a structural framework. Okay. Okay. And so this structural framework not only provides the supports that's needed for the human to perform its daily actions, but it also provides protection for a lot of the softer tissues in the body. Okay. Okay. And so that's the first main purpose. And so that's, I think, the one that people generally think of when they think of bones. Okay? And so the other main purpose that bones serve is that they form basically a bunch of rigid levers within your body. Okay. And that's important because it basically provides a place for your muscles to attach to. And then once your muscles attach to the bones, it can then use them to kind of move move your body and to do other stuff. Okay. Okay. All right. And so, if you had to kind of characterize what bones do for the human body, I'd say those are kind of the two main ones. Okay. And so based on this description here, and I think kind of just based on our intuition for how we understand bones are often seen as these kind of very hard, rigid structures within the body. Okay. They come in lots of different shapes and sizes. Okay. And each bone has its geometry kind of morphed or designed for its specific purpose. Okay. Right. And just like any other system of your body, maintenance of your bone health is extremely important for every individual. Okay. And this is especially important as you age. Okay. Because what tends to happen is that as you age, the bones itself kind of become they lose a lot of its kind of structural integrity. Okay. And so probably, if you watch any kind of daytime television, you've probably heard of the condition called osteoporosis. Okay. And so we'll be talking about that condition later on, but basically it's a condition where your bones lose a lot of its calcium or mineral content and thus loses a lot of its strength, making you a lot more susceptible to things like fractures and things like that. Okay. And so if you have any kind of injury to your bones, it's going to make movement or just, any kind of physical action a lot tougher. Okay. Not only for the pain, but just also from a stability standpoint as well. Okay. And so, we're not, because this is, an engineering biomechanics class, we're not going to go into super great detail about, of all the bone structural data and things like that. But, again, my goal is to kind of provide you with the kind of the functional information that you need in order to, design devices for bones. Okay. Because there's a lot out there. There's a lot of medical devices and medical treatments that are out there that support bone health, either, structural devices that kind of offload some of the stress that the bones experience, or even medical therapies that engineers contribute to help bones heal from injury. Okay. All right. Any questions so far? Okay. All right, question in the chat. So would I recommend older folks to strengthen the bones by lifting weights? Yeah, that's a good that's a good question. Um, and so, we'll be talking about, later on about bone remodeling and how the bones itself can strengthen over time. And so, lifting weights actually does help, your bones strengthen, because what you do by there is you kind of stress the bones, and the bones itself kind of react and say, hey, we experienced this large load, maybe we should get stronger. And so doing things like weightlifting or even just, regular light exercise, it really helps a lot in strengthening your bones. But, that process is, it's a lot more effective when you're younger. And so when you're older and you do those kinds of weight bearing exercises, I think the risk that you run is that, first of all, you might injure yourself, depending on the nature of the exercise. But also just the natural processes within your body that actually strengthen the bone are actually a lot slower when you're older compared to when you're younger. So, it has some benefits, of course. I mean, physical exercise is good for a lot of different reasons. But in terms of bone health, it's not as effective as you age. Yep. Mm-hmm. Right. Any other questions on this? Okay. All right. So let's talk about the composition and structure of bone tissue. Okay. Right. And so, before we talk about kind of the chemical composition, let's kind of talk again about, what bones need to be in order for it to accomplish its goal. Right. And so we know from the previous page that bones need to be strong. Okay. Okay. Just because, we expect the bones are going to be, carrying a lot of the weight or a lot of the loads for our body. Okay. So they need to be of some kind of material where it's, we can have confidence that it's not going to break under any loads. Okay. But, another important quality that bones need to have is that they also need to be pretty lightweight as well. Okay. Okay. Because remember, your bones are the main thing that your muscles are attaching to. And so when you swing your arms or you perform any kind of movement, it helps a lot if your bones are lightweight so that you don't kind of feel that, so you don't feel that force, right? And so if your bones weighed any more than they do, it would take a lot more force from your muscles to either lift your arms or to walk or things like that, okay? And so the main things that, that you're looking for bones that, they're strong and lightweight, okay? Right, and so the way that the material constituents within bone and the way it's kind of arranged kind of helps to accomplish both of these goals. Okay, so let's talk about kind of the major minerals and the major materials that make up bone. Okay. Okay. Right, and so the first major constituent is calcium carbonate. And so I think we've all seen the commercials, or maybe your parents have told you growing up to drink a lot of milk, right? Because milk contains a lot of calcium, and calcium is good for your bones. Okay, so that wasn't fake news, and so that's true. Okay. And so another kind of molecule of calcium that's in your bones is called calcium phosphate. Okay. Okay. So calcium's kind of used in both of those quantities, and these quantities here, both of these calciums, they're what's known as kind of the strengthening minerals for bones. Okay. Okay. Right. And so these are the chemicals that basically give your bone strength. Okay. right? And so calcium, calcium is a mineral, right? And so calcium gives your bone strength. So the more calcium that you intake, a lot of that can go to your bones to make them strong. All right, and so the other two constituents in bones that are important to know are collagen and water. And so if you've never heard the term collagen before, collagen is a type of chemical that's within your body, and it's used to make up a lot of the tissue in your body, right? And so it's going to be in bone, it's going to be in your muscles, it's going to be in the and a lot of your soft tissue. So lining the edges of your lungs, of your blood vessels, and so it's a very abundant material in your body. Okay. And what these typically do is that these provide your bones a little bit of flexibility. Okay. Okay. And so there's not as much collagen in bone as there is in other tissues, but if you can imagine, think of your lungs, or think of your blood vessels, right? And so when we think of those tissues, we think of them as kind of flexible materials. So your lungs have to kind of expand and contract, as you breathe in and out, right? And so collagen is this kind of like stretchy, I think of it almost like rubber-like material that kind of aids in kind of flexibility for your tissue. Okay. And so even though there's not that much in bone, there's still some in there, right? And that flexibility actually is a really, really important quantity for bone as well. Okay, not as important and not as abundant as the minerals, but it is really important. Okay. All right. And so the next question I think is how much of these quantities are actually in a typical bone, right? And so if you look at each of the bones in your body, each of them are going to have different chemical compositions, but we can kind of say in general how much minerals are in there and how much collagen and how much water. Okay. Right. And so for a typical bone, 60 to 70% of its weight, or I should say dry weight, 60 to 70% of its dry weight will be comprised of the minerals, so the calcium carbonate and calcium phosphate. Okay? And so calcium you can see is the primary constituent. Okay. Water is going to make up about 20 to 25 to 30% of a typical bone weight. Okay. Right, and then collagen kind of fills in everything else. Okay. Right. And so just as kind of a trivia aside here, right? And so we know this quantity right here because scientists have basically picked up bones from the ground or picked up bones from cadavers, and they kind of measure the composition from that. Okay. But this is dry weight. Okay. And so what tends to happen that once the bone is taken out of the body, it tends to dehydrate very quickly. Okay. And so that 60 to 70% number is with all the water kind of evaporated from there. Okay. And so if you want to kind of measure kind of the true material qualities of bone, you have to do it with it properly hydrated. Okay. And so this I think the tempting thing here is to kind of add these two numbers, so the 60 to 70% plus the 25 to 30%. Okay. But it's not exactly that. And so the collagen kind of is higher, has a higher percentage of weight compared to these numbers than what these numbers indicate. Okay. And of course there's other stuff within the bones as well. There's kind of some empty spaces, some blood vessels run through there, and so there's blood that contributes to this too. So these are kind of, you can kind of think of these as rough numbers. Okay. All right, question. So when I say dead weight, does it mean the muscles and fluids stop assisting the movement of the bones? And so dead weight, it's mostly just water, honestly. Like it's a lot of the water that comes, a lot of it's in the blood that flows through the bones. That gets kind of dehydrated very quickly. When you take the bone out or it dries up. And so when people say dry weight, they mostly mean that it's devoid of any water. Yeah. Mm-hmm. All right, question. So are bones linearly elastic? They are not. And so I'm going to try to get to it today, but we'll talk about kind of the elastic properties of bone and how you can characterize its elasticity, but they're very not linearly elastic. Yeah. The short answer to that question is that your bones have to be a lot stronger in compression and tension than they are in shear, because the way your body is designed, if you think of yourself kind of standing up like this, most of your bones and the weight that they bear, your bones are almost always going to be in compression. And so it's pretty rare that your bones are going to be in shear. And so, your bone can kind of, it can kind of shift a lot of its strength. So it doesn't have to be as strong in shear, and it can be more strong in tension and compression. Yeah. Mm-hmm. Yeah.
When would you go in a situation where the bone is like under shear, like some sort of twisting?
Yeah. Yeah. Twisting is a big one. And so whenever you put any kind of external torsion on a bone, then that's going to put a torsional shear on the bone. Or even a more extreme case is something that that's kind of maybe cleaving through your arm like this. That's maybe causing the bones to like go like that. That's another condition with shear. But I think torsion is kind of the more common case for most people.
Like when you're like screwing in a screwdriver, like turning your wrench or something like that, you're putting shear on.
Yeah, exactly. Yeah.
And breaks happen easier that way.
So
something like say for example, like if you were to turn a wrench too hard or something, like if the nut was stuck, could you actually fracture your arm if you try to turn the wrench too hard?
So for an action that you're kind of controlling with your muscles like that usually doesn't put that much torsion on your bones, because a lot of that torsion is taken up by like the muscles, because you're actively using your muscles to perform that action. Usually, if your arm's kind of twisted in a way that's kind of unnatural to you without you kind of exerting your muscle to do that, that's usually the one you're going to be more at risk for, like a shear fracture. Yeah. Mm-hmm. Question? Oh, yep. Mm-hmm. All right. Any other questions on this? Okay. 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 All right. And so another important quality of bones that I want to talk about is something called porosity. And so have you guys heard the term porous before? So you guys probably are kind of aware of like something like that looks like Swiss cheese or maybe like a sponge, right? And so porous basically is just referring to how many little holes or little air holes within the bone, okay? And so bones, even though we just talked about, it's made of like calcium carbonate and it's made of water and collagen, your bone has a lot of empty cavities. Okay. And so kind of the visual that, that I think of, and, usually if you look up kind of bones, on the internet, it kind of almost looks like a spongy kind of material. Okay. Okay. Right. And so basically the more porous a bone is, or the more porous, a section of bone is, the less, it's basically, it's going to have more of these tiny holes and less space for, the minerals or other materials. Okay? And so from that statement, you can kind of conclude that, you know, the more porous a bone is, the less strong it's going to be, right? And so I'd say the less percent volume of there is of things like calcium carbonate or the other minerals, then it's just going to be naturally a weaker bone. Okay. You know, which doesn't seem great, right? Because we've known that, you know, bones have to be kind of strong and rigid in order to perform this task. But actually having some flexibility and some porosity can actually be of benefit to certain bones, or more specifically to certain portions of bones. Okay. Okay. A question in the chat. All right, question. So do these pores affect the strength? Like if there's a fracture, will have a bigger crack propagation? Yeah, so generally, you know, the more porous you are, generally you can expect it to be less strong. You know, and so, you know, those types of bones will fracture a lot more easily. You know, in terms of crack propagation, I actually think it'll actually, you know, more porous bones might actually dampen the crack propagation, because what tends to happen is that the more porous your bone is, it actually becomes more sponge-like, right? And so more spongy materials, as we know, are kind of they're less brittle. Okay. And so if you're less brittle, then you're kind of less likely to crack, and you're kind of more, you can handle kind of more kind of harder impacts. Okay. And so actually bones actually take this to use this to their advantage too. And so, you know, certain bones that, you know, that have to be a little bit more flexible, they can do that by affecting the porosity of that bone. And so actually, let me talk about kind of the two characterizations that we have for porosity, and then we'll kind of get into a bigger discussion of, you know, how these are used. Okay. Okay. And so the first classification is a cortical bone. Okay. And so cortical bones are your bones with very low porosity. Okay. And low porosity is characterized with about 5 to 30% of its volume occupied by non-mineral tissue. Okay. And so these bones will be predominantly, you know, made of calcium or you know, of all those other minerals. Okay. Okay. And so due to its high mineral content, cortical bones tend to be much stronger and stiffer. Okay. Stronger and stiffer compared to the next bone that we'll go over. Okay. And so this allows these types of bones to sustain, you know, very large amounts of load and not fail. Okay. And so that's cortical bone. And so the next type of bone is known as trabecular bone. And so trabecular bone is the opposite of cortical bones. And so these guys have high porosity. Okay. And so high porosity is characterized by 30 to 90% of its volume occupied by non-mineral tissue. Okay. And so these trabecular bones, these are the ones that kind of look like a sponge. Okay. Okay. Right. And so these bones, because they don't have nearly as much mineralized tissue, they're they're going to be a lot weaker and a lot less stiff. Okay. But these trabecular bones have they're much more flexible. Okay. Okay. And by being more flexible, it can sustain larger amounts of strains before it fractures. Okay. Okay. Right. And so trabecular bones, these are actually really great at either bones that are going to be sustaining a lot of impacts. Okay. Or maybe even just at a section of bone that's going to be sustaining a lot of impacts. Right? And so I'll show you a figure of this on the next page. I'll draw one. But even for like a typical long bone, so say like your upper arm bone or like your thigh bone, right? What you'll see is that if you cut it open kind of near the ends of the bone, you'll actually see a much higher, a much more trabecular bone than cortical bone, because what happens at the ends of your bones, that's where it kind of meets other bones at the joint, right? And so what can happen a lot is that these bones kind of sustain a lot of impacts, right? Especially if you're doing kind of pretty high, high intensity physical activity. And so it helps for the ends of the bones to be more trabecular, because when you're sustaining all these impacts, you're getting a lot of these kind of micro strains and micro impacts. And so it helps prevent the ends of your bones from fracturing, because those are the ones that are going to be they're going to be impacted and compacted a lot more than the cortical bone. Okay. And so at the end you'll see trabecular bones, but in the middles you'll see a lot more cortical bone, because that's where it gets all of its strength. Okay. Any questions on this? Yep.
Can you develop more porous bones, or just like specific design the bone structure?
Yeah, that's a good question. So and so it's not something that you can kind of actively control yourself, but you can kind of influence it kind of externally from depending on how much physical activity that you do. And naturally what tends to happen as people age too is that a lot more of your bones become more trabecular, just because you lose a lot of your bones kind of naturally kind of lose mineral over time. And so it's not something that you can really control, but it does change over time based on some factors. Yeah. Mm-hmm. Okay, so let me draw you guys kind of an example of a long bone, and I'll show you kind of how trabecular bone and cortical bone is typically distributed. Right. And so a long bone is like kind of the bone that people usually think of when they think of a bone, okay, in general. And so these are the bones that kind of make up your limbs, okay? And so your arm bones, your leg bones, they all kind of have this structure where it's kind of long, it's a long cylindrical shaft, okay? So like I talked about, on the previous page, the ends of the bones here are kind of where it's going to contact other bones. Okay? Okay. And so as you go about your day and as you kind of perform physical activities, the ends of the bones are going to be contacting other ones. And so it's going to be sustaining kind of a relatively high force impacts, depending on what you're doing. And so it actually helps a lot to have kind of pockets of trabecular bone in these, in these sections, okay? Because in order to kind of sustain those impacts, you want something that's kind of, relatively flexible. That's not going to brittly break, right? And so think of like the shock absorbers on your car, right? And so when your car sustains kind of sudden impacts, like you drive over a speed bump or something like that, you want some flexibility in it, right? So you don't want the car just be completely rigid, because if your car was completely rigid, you drive over a speed bump and everyone just kind of just goes all over the place, right? You want a little bit of flexibility in there so that you can kind of, soften those impacts and kind of distribute them out over a long period of time. Right? And so kind of the trabecular bones over there serve that same purpose. So it's almost like kind of internal shock absorbers within your bones. Right? Whereas the middle of the bone, which that doesn't have to worry about the impacts, as it's not contacting anything else, these are mostly made of cortical bone. Because that's where the bone's going to get a lot of its strength. And so, the ends of the bones have to sustain kind of these short-term impacts as it contacts the other bones. But in terms of, long-term, weight bearing or kind of, in terms of getting its strength, the middle of the bone can be made of cortical bone in order to kind of sustain these long strengths. Okay. Okay. And so that's a typical long bone there. Okay. But of course, there's other bones in your body that have different shapes and different functions. Okay. And so if you think of like a spinal bone, or maybe like a bone in your vertebrae. Okay. Your vertebrae is constantly absorbing these shocks, right? And it's also you have a lot of spinal bones, right? So you have a lot of bones in your vertebrae. And so it's contacting other bones quite a lot, and it's also subjected to a lot of high impacts as even just walking, you kind of put a lot of stress on your spine like that. And so what you'll see from your vertebrae bones is actually, these are almost they're mostly dominated by trabecular bone. Okay. All right. Any questions on this? Okay. All right. And so now let's get into the elastic properties of bone. Okay. So this is kind of the sequel to kind of the very beginning of the class where we talked about stress and strain. Okay. All right. And so at the beginning of class, I showed you this relationship here. Okay. Right, where we had stress and strain are linearly related. And so this is for a linear isotropic material. Okay. But, as I kind of mentioned before, is that bones are not linear, or actually, you can consider them linear, but they're not isotropic. Okay. And so bones are what is called an anisotropic material. Okay. And basically, what this means is that the strength and the material properties of bone depend on which direction the mode is applied. Okay. And so we talked briefly about this kind of at the beginning of lecture today, is that, you know, bones have to be much stronger in compression and tension than they are in shear. Okay. And even more specifically, you know, bones have to be much stronger in compression than anything else. Okay. And so this complicates our description of the material. Okay. Because I think, you know, up to this point, when we talk about, you know, material properties, we usually only worry about just a few different parameters. Okay. And so in the simplest case where you have a linear isotropic material, you know, the only properties that you need are things like the Young's modulus, the Poisson's ratio, and also the density. Okay. And so that's three properties. And so that's relatively few. Okay. But for an anisotropic material, you need a lot more material property that basically tell you the strength in all the different directions. Okay. And so the question is, you know, how many more material properties do we need? Well, it depends on the material. So in the worst case, you can have up to 36 different material properties. Okay. So that's the absolute worst case. But thankfully, you know, very few materials are actually fit into that category of absolute worst case. And so usually for most anisotropic materials, you're probably in the ballpark of like, you know, 9, 10, 11, 12 different material properties, which is still a lot. It's still a lot more than 3, but it's more manageable than 36. Okay. All right, and so the main reason, you know, we characterize bone as such is that, you know, bones have to be much stronger in compression than all the other directions. Okay. And so, you know, if you want to get really, really technical, kind of the consensus right now in the research community is that bone is actually not an elastic material. It's actually characterized as a viscoelastic material. And so if you've ever heard that term before, it's basically a material that kind of exists kind of in between the realms of a fluid and a solid. And so it's something that, you know, I admit that I only know kind of a surface level understanding of it. But basically, you know, the idea behind that is that, you know, bones, they exhibit some kind of flowing characteristics, right? And so kind of the big difference between a solid and a liquid is that when you apply stress to a solid, you know, it's going to deform, and it's going to deform very quickly, right? And so you apply stress to a steel rod, and so it's going to deform. It's going to do so very quickly. Okay? But if you apply stress to a fluid, you know, it's going to flow, right? And so there's an aspect of time of you know, after you apply the stress compared to how the material itself is going to react, right? And so for fluid, it takes some time. But, you know, if you keep applying that stress to a fluid, it's going to keep flowing on forever, right? And so if you apply gravity to water, it's just going to keep flowing and flowing and flowing until it hits the ground, right? And so a viscoelastic material kind of exists kind of in between these. And so for a viscoelastic material, when you apply stress to it, you know, it's going to deform, you know, but it's going to take a little bit of time to deform. So you'll apply stress, and then it's going to react maybe, you know, maybe half a second later or something like that, right? But, for a viscoelastic material, that deformation is finite. And so, it's going to reach a point where it's not going to deform anymore. Right? And so technically, if you want to be really technical, bones are considered viscoelastic. But that makes it a lot more difficult to analyze because viscoelasticity is something that's still, I would say, pretty much being very heavily researched and being very heavily characterized and parameterized by the research community. And so we'll just for the sake of this class, we'll assume that bone is strictly just a solid and it's going to deform and act like as such. But right now, kind of at the very cutting edge, they're studying, what they're studying is kind of the viscoelastic properties of bone, how to characterize that. Okay, so any questions on this? Okay. Okay. All right, and so for a kind of linear isotropic material, we had that relationship between stress and strain on the previous page. Okay, but for an anisotropic material, the relationship between stress and strain kind of has this form. And so I'm kind of drawing the very shorthand notation here, okay? Where this sigma I right here, this is a 6x1 stress vector, okay? And so this epsilon j, this is the 6x1 strain vector. Okay? And so all this, this notation might be, you might not have seen this notation in a previous class because when you think of stress, you think of strain, you think of like its tensor representation, right? So normally you think of it as a 3x3 matrix. This kind of takes the 6 components of stress and kind of just puts them in a line on a vector. And so it's not very standard, and so it's it's not. I would say it's not the standard way to represent stress, but it makes this representation a lot easier than it could be. And so if you're curious, about what this sigma I looks like, it looks something like this. And so you'll have all the normal stresses up top, and then all the shear stresses are on the bottom. But this is not so important for this class because we're not gonna dive into the nitty-gritty of all the different stress components. Okay, right. And so if you remember from last week, normally we arrange these stress components into a 3x3 matrix, but here they just stack them up together as a vector. Okay. All right. And so the key quantity here is this guy right here. Okay. And so what this is this is a 6x6 matrix of elastic constants. Okay, and so this is the guy that's replacing our Young's modulus from the previous page. Okay, and so instead of having just a scalar number, just one number that represents this, now we have this 6x6 matrix that basically represents every possible combination of stress and strain, that there is out there. Okay, because the thing with anisotropic materials is that different components of the strain can affect different components of the stress. Right? And so for a linear isotropic material, basically what you have is that the only strain that's going to affect a certain component of the stress is that those two have to be matching. Okay, but for an anisotropic material like this, you can have any component of the strain affect any component of the stress, and the way that they're related is through this matrix. Okay. And so kind of in the classical form for this equation, in case you're curious, if we kind of maintain that stress is a 3x3 matrix, okay, it looks something like this, okay? Where this sigma ij here, this is the normal 3x3 stress tensor. This epsilon is the 3x3 strain tensor, okay? And then this IMNJ right here, this is what's known as a fourth order tensor. Which I still can't even wrap my head around even to this day. So, you know, you kind of know the difference between 2D and 3D, right? And so in 2D, you know, things look flat. 3D, you know, 3 you kind of add a third dimension. This is like a 4D construct where you have like a 3D kind of cube, and then inside each cube you kind of have another dimension inside there. So it's messy. So I personally prefer this kind of representation up here, just because it's a lot easier to kind of visualize and a whole lot easier to draw as well. Okay, and so let's talk about this. Matrix of elastic constants right here, because that's kind of the main thing. Okay, and so you can see up there that it's a 6x6 matrix. Okay, and so we can represent it as something like this. Okay. Right, and so each, you know, in kind of the most general case, each entry in this matrix can be a different number. Okay. And so, like I mentioned earlier, that, you know, there's 36 different constants in here, and so you can have 36 different, you know, material properties for a most general anisotropic material. Okay. And so that's tough, and so that's normally kind of way too much to account for, you know, just on its own. Okay. And so usually when you have a material that's not isotropic, usually you can make some assumptions to simplify this matrix. Okay. Okay. Right. And the nature of the assumptions that you're going to make is they're basically going to be symmetry assumptions. Okay. And so, you know, even though you're saying that, you know, everything's not isotropic, there's still some symmetry in your material that you can take advantage of to simplify this matrix. And that's going to simplify things quite a bit. Okay. And so on the next page, I'll give you kind of the two most common assumptions that people use for characterizing bones, and how that simplifies this matrix. Okay. Any questions on this so far? Okay. All right. All right. So the first assumption, the first symmetry assumption that we'll make is we'll assume that the material is what's called transversely isotropic. Okay. Okay. And so what that means is that the material properties are not going to change when you move around the long axis of the bone. Okay. Okay. Right. And so if you kind of draw a typical long bone like this, okay, it's approximately cylindrical in shape. Okay. If you travel around the bone in this direction, okay, and so you basically kind of walk around kind of the outside of the bone, and you kind of go in a circle, you know, you're not going to see any change in material properties. And so that's basically all that it means. Okay, and so if you do that, then the matrix of elastic constants simplifies pretty significantly. Okay, a lot of them turn to zeros, and in fact, a lot of other quantities kind of are mirrored to each other. Okay. And so if you apply this assumption, then your matrix of constants looks like you have C11 up top, C12, C13. Okay. But the rest of the first row are all zeros. Right. And so the second row will be C12. Okay. And then by making this assumption, you're basically saying that C22 is the same as C11. And so those two are going to be the same. Okay. And you're also going to say that this third entry right here is going to be the same as what's above it. Okay. So that's going to be C13. And the rest of it's going to be zeros as well. Okay. And then the last row and the third row of the matrix is going to be C13, C13, C33. Okay. Yeah. No, so it's and so based on the assumption that you're making, it's instead of C23, we're saying it's the exact same as C13. And so that's why. And so there's, I'm repeating some numbers here because that's kind of based on the symmetry that you're assuming. Yeah. And so you have C, so all of these guys right here should be C13. And then these two should be the same. So these will be both C12. And then these ones are C11 and C1. And so all of these should be the same, just in, and that's based on the symmetry arguments that you're making. Yep. Mm-hmm. All right. And then the rest of the matrix looks like the following. Okay. All right, so if we count the number of unique entries that we have here, I'm going to try to see if I can use a different color for each one. All right, and so if we count all the different colors, what we have here is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. And so this is a lot less than than 36 that we had before. Okay, so this is a pretty powerful assumption that you can make. Okay, and it simplifies your your characterization of the material really significantly. Okay. Unfortunately, this is kind of an awkward time to stop this, but we are out of time, unfortunately, and so we'll pick this up on Monday, where I'll show you kind of the other kind of characteristic of these materials called orthotropic. Okay, and then I'll start to give you some numbers about what you can actually plug in here, so that you can actually characterize bone materials. Okay. Okay, and so thank you guys for coming today. Thank you guys for tuning in. Thank you guys for coming in person. Have a great weekend. Even though the last time I saw you guys, I said the same thing, but have a great weekend, and I'll see you guys on Monday. Hey. Okay, cool.
How exactly would you give like a dictionary type definition for eigenvectors eigenvalues, because I couldn't find like a satisfactory one that I wanted.
Yeah, so what I wrote was I kind of wrote out the equation for it. So AX is equal to lambda X. And I said that eigenvalues and eigenvectors are kind of special vectors or special values for a given matrix that satisfy this equation.
Okay, that's what I was thinking.
I think that's the the definition is a lot more mathematical than this kind of anything else.
It's AX is equal to lambda X, right? I
Yeah.
always think of it as, what is it, the determinant of?
So that's how you find that's how you find the eigenvectors. And so you set up the way you actually solve for is you set up that system and then you find the determinant of that. You set it equal to 0, and then that's how you.
What did you say? So you said the formula and then.
Yeah, I said then lambda and X are basically special properties of the matrix that satisfy this relationship.
It's not stapled, is that okay?
That's fine. Just fold it from there.
Oh, and then don't mind this. This was like, I had to get a bunch of different screenshots and I had everything in order and then I had to go back and like take screenshots. That was for the other assignment because I was trying to like figure out, okay, how am I gonna put them in the Word document like in order so they're not just all over the place. Are we gonna do another ANSYS activity today or?
We are. Yep, we're going to do our next activity today.
Is that how it's gonna be like every time? The class after we turn it in, we do another one?
Yeah. So my cadence right now is every other week we're going to do an activity. And so for 540, I have 8 activities planned, and so that's perfectly set up. Every other week we do one. David, did you have any other questions before I close the call?
Should I put EGME